Okay, good afternoon, everyone. It is with great pleasure and pride that I welcome you all to this faculty development program on quantum sensing. I would like to extend my welcome to the chairman, AICT Academy, and director, MNIT Jaipur, Professor N.P. Padi, our chief investigator, Professor Vineet Saula, who is present here also, and our co-chief investigator, Dr. E.S. Pilli, and my HOD and joint principal coordinator for this program, Dr. Kamlendra Awasthi. On behalf of the organizing committee, I extend a warm welcome to all distinguished speakers, invited experts, and all the participants, faculty members from institutions across the country. Your presence and enthusiasm reflect the growing interest in quantum technologies and more specifically the transformative potential of quantum sensing in various domains. So far, more than 800 participants had joined for this FDP. It shows the enthusiasm on the importance of this topic. We are indeed living in a time where the boundaries between physics, engineering, and computation are becoming increasingly blurred, or you can say overlapping. Quantum sensing is rooted in the fundamental principles of quantum mechanics, is not just theoretical pursuit, but it is a rapidly emerging technology with real world applications. Specifically, it offers unprecedented sensitivity and precision in measurement, opening new frontiers in science and innovation. This FDP has been thoughtfully designed to provide participants with a comprehensive overview ranging from theoretical foundation to practical implementation of quantum sensors. Through expert lectures, collaborative discussions, we aim to foster a deeper understanding and to equip you with the tools necessary to bring this knowledge into your teaching and research. I would like to take this opportunity to thank our eminent speakers for graciously accepting our invitation and for sharing their expertise with us. Your insights will no doubt inspire and enrich our collective learning experience. To our participants, I encourage you to engage actively, ask questions, and make the most of the interactions throughout this program. Let this be a platform for not just learning, but for building future collaborations and networking. Once again, I extend my heartfelt welcome to one and all present here, including the organizing team for this FTP. And let us embark on this exciting journey into the quantum sensing together. Now I would like to invite Dr. Kamlendra Awasthi to give a brief introduction to the program and to the speakers. Sir, please.
Thank you, sir. And I welcome all our speakers, participants for this program. Somehow, this is the program that we have maximum holidays. So this was the challenges to cover all the lectures and between this thought spam. So we tried to connect with our eminent speakers, and I'm thankful to them for accepting our invitation. So we are able to have speakers of across the country and who have different expertise in the quantum sensing. So we whatever the syllabus that is prescribed from AICT on the quantum sensing, we little bit elaborated so that we could cover each aspect of the curriculum. And some things you may find like this is more elaborated, and we have discussed with our speakers, so like it is well connected. So we will try from like with fundamentals, and then we will go for the application part. So now I go just to introduce the speakers for our meeting. So uh, So just first speaker, he's like speaking today also, this Professor Rajan Jha. He's from Department of Physics, IIT Bhubaneswar, and his research interest in the coupling photonic nanostructures, instrumentation for industrial application, and quantum interferometer, and flexible and variable photonics and plasmonics. And he's covering these three lectures for your FDP on your sensing technologies, requirement of high resolution sensing, and engineering and physics, and also biological medicine, aerospace, and the mobility. Second speaker, Dr. Aswat Babu H. I came to know like the maximum participants, some of them they are repeating on this FDP. So I hope you are already familiar with Dr. Aswat Babu. He is from Triple IT Dharwad, and he has an interest on quantum information theory, quantum optics, nonlinear optics, and nonlinear dynamics of optical system. So he is going to introduce the concept of sensing, then fundamental quantum mechanical principles, quantum measurements, and will cover this quantum photo detection. Next speaker will be our Dr. Vaibhav Gupta. Right now, he is in Center for Quantum Science and Technology at IIT Mandi. He has research interest in plasmonics, photonic integrated circuits, quantum optics, self-assembly, and he is going to introduce the concept of this photo detection, fundamental limits of photo detection at quantum level, and he will introduce the linear detector and coordinate measure. Another speaker, Dr. Richa Goyal from Quantum. She did PhD from IIT Bombay, and she's going to speak on quantum sensing technology challenges and the future perspective. And another speaker, or maybe the last talk, will be Dr. Kausalya from Department of Physics, IIT Roorkee, and she will be speaking on this quantum information science with telecom-based quantum emitters in silicon. So we tried to have a speaker like so that they could cover from fundamental and they could cover the most application part on this in quantum sensing area. I hope you will enjoy the sessions with the speakers. Please feel free to interact with them and post your queries or question after the session, and we will like to discuss with them with the speakers. So thank you once again for joining this course, and we will try our best to deliver the content with these eminent speakers across the country. Thank you very much. Now I request our co-chief investigator, Dr. E.S. Lilly, to say a few words about this FDP and interact with our participants.
Yeah, apologize for the small disturbance here because of we are having some power issue morning and it is being rectified. But we are sorry for that inconvenience. So at this time, I'm very happy to be here before all of you, and we are very thankful that you are all continuing to pursue this course because we are now in the 7th course. Of course, the 6th in the number that we are offering, but 7th in the course that it is going to happen as per the AICT syllabus. We have clubbed 3 and 4 together. But we have had immense response from all of you, and this time also more than 800 have registered in other academies also. We have academy participation from IIT Kanpur, IIT Guwahati, IIT Roorkee, and IIIT Jabalpur. So 5 institutes are coming together, and we are hoping that we get the endorsement from National Quantum Mission also. AICT is has endorsed and working with them, and hopefully by the end of this course we'll give you the details of how the certificates will be issued and when the physical program will be conducted. So kindly give me some time because you've been watching me saying this for a long time. I also feel a little bit disturbed, but from MNIT side, to issue the PG diploma, we can do it immediately after you complete 6 courses. But we are just waiting for the AICT PG certificate, which will be more valuable and it will be more useful for all of you. As this has picked up, many people across the country are benefiting from these courses. I request a kind of course, some of you may, those who have finished the QT-5 and 6, you may be little upset that we have made the attendance requirement a little bit stringent. So kindly bear with us. That is only to ensure that you attend the course and take the exams and finish the things on time. So we are sharing the YouTube links with you every day. So please watch the videos whenever you miss out. We are just looking at a bare minimum of attendance. In fact, we are not looking at 75% attendance. So at least some level of attendance should be maintained by all of you. So that is one concern, because otherwise just passing the quiz exams, we will have the certificate. We'll have one quiz, mostly starting on Friday, Saturday. So next Friday, Saturday, Sunday, you will have the first. So that schedule, Dr. Manoj will be announcing, and he will be facilitating that. My sincere request to all of you is that all of you take the classes very seriously. please try to be present mostly between 2 to 4. And whenever there is some emergency which you are not able to avoid, you please attend to the YouTube session immediately after. Prepare well. And now that we should not think that quantum communication is over and these topics are not important, because National Quantum Mission has put 4 verticals. Quantum computation is the first vertical, quantum communication is the second vertical. The third vertical we are seeing now is quantum sensing, and fourth will be quantum materials. So QT-08. So these 4 form the crux of the 4 verticals that National Quantum Mission is looking at, right? So please wait for the announcement of the physical interaction that will be held. Maybe after QT-07, we'll have time to have the physical interaction where you will take the written exam, and after that we will make the announcements of the certificates issue. So we request you to complete 6 courses in all. So that's something which we would like you to complete. So totally 18 credits. I welcome all the resource people who have joined. So Dr. Arup Samantha, Dr. Kaushalya, and of course I wish the best wishes to the coordinators who are running the program. I was part of the first 4 programs. It was a joy to have helped you through that. Now we are having Dr. Manoj Kumar and Dr. Kamalendra Avasthi from physics department, and they are very much working in the area of quantum physics. And that's why you can see that apart from the IBM experts who are coming, like Dr. Richa Goel and Dr. Ashwath, who is an IBM educator, we have faculty coming from IIT Mandi, IIT Roorkee, and also other institutes which are dealing with quantum sensing research. So it's a joy once again that we have put this program before you, and I hope that you will make the best use of it. So just taking the exams, just getting the certificate is not the issue. Gathering the information, collecting the material, and of course, one of the vision that we have of the Electronics and ICT Academy at MNIT Jaipur, and also the 6 other institutes, our vision is being fulfilled. We are putting the content ready. We are having the slides, we are having the material, we are having the video recordings with you. But our job is done. But if you don't gather that information, if you don't use that information, ultimately you and partly we will be the loser, right? So I request all of you to take these classes very seriously, because most of the faculty members, as you have seen, they have taken a lot of pain to put the material together, to make it very convenient for you to listen and understand. So I wish that all of you will make the best use of it. Some of you are not able to join on these sessions at this time. We have shared the YouTube link. Please join on the YouTube link. We will sort out the other issues after the end of this class. Thank you so much. Thank you, Dr. Manoj, for giving me this opportunity.
So now I request
of programs which are logistic specific, and we have usually participant exceeding 1000 per any quantum program that way. I think that speaks well of the design programs and well of the speakers delivering continuously right from the January 25. So thanks to all of these speakers, experts, for their valuable efforts and having agreed to actually address our participant program that part that way. And it comes to the part of role which we here is E.S. Pilli has a series of quantum programs, and credit goes to him for many other things. As a Pilli certification, if you complete 18 credits, specific programs on quantum. So we'll put a kind of form. We'll fill up your details and we'll take care of that part. And this is not just one attempt of, this is only one attempt of all academies. Triple IT Roorkee, Triple IT, I'm sorry, IIT Roorkee, IIT Kanpur, Guwahati, NITs at Warangal, Patna, and ourselves at Jaipur, and Triple IT Jabalpur. We have taken up such series in different fields. So please have a look at our websites of any of one of the academies and just see if other programs are also of interest to you or to your colleagues. That way you can publicize. So welcome you all. I wish you happy learning. And again, thank all the experts. Some of them are present here. Dr. Ashwath is well with us for a long series of their programs. A special thanks to him for being always there for us that way, and other speakers who are participating in this program. So I take rest here and give back to Dr. Manoj Kumar for next question. Thank you very much.
Okay. Thank you so much, sir. Yeah. Indeed, it is a wonderful series, and to have such vision to conduct such FDP and skill development programs through EICT Academy. Now, I would like to invite uh, some of the speakers who are here, maybe Dr. Aswath Babu, to just share his views on this quantum sensing FTP. Aswath sir.
Very good afternoon to the the organizers, Manoj sir, Ili sir, and Avasti sir. Thank you so much for a kind invitation and opportunity for me to share the knowledge which I learned along the way during my PhD and so on after that. So yeah, I would like to reiterate what Ili sir actually mentioned. So if you can continue to attend the sessions, or by any means due to some other engagements if you are unable to do, so you please ensure that you listen to the recordings available later. It's not just listening, you would also get attendance out of it. So that's something useful for you as well for your entire program. So yeah, please take it in a positive sense, the attendance compulsory, because as we always impose on our students to attend all our classes, okay, so it's not fair if we are not following ourselves. So yeah, it's an upcoming field, so there are so many things being discussed throughout all the QT modules. So there is nothing waste or nothing unimportant. So everything going to add somewhere here and there. For example, some of the things which I'm discussing for today, which are the part of the course which I was teaching like 5 years back. So in a way, some whatever we learn, whatever we prepare for something or somewhere else would get useful. So I once again congratulate all the participants for taking a positive forward step to join this QT and putting your time for learning new things. So I wish you all a happy learning, and I would always try my very best to make myself available and also myself more informative, whatever I could from my ability. So thank you once again, one and all. So I wish and congratulate the organizers also for going with this marathon of FTPs with the Atal AICT support. So thank you very much once again, everyone. Have a nice day, and we'll see with my session. Over to you, sir, Manoj sir.
Okay, thank you so much, sir. And Yeah, indeed. We learned so many things from you, and maybe I can also request Dr. Kausalya to share her views. She is also online. Kausalya, madam. Okay. So, nee. Fine. I think we should. Okay. So, it looks like we come to an end for this inaugural session. There were some issues with the power here, and we are struggling since morning. Billy sir has already mentioned, but now the power is restored and we will have seamless session. So stay there for the session. I would like to welcome our Dr. Aswat Babu. Maybe he can start just after this session. So over to you, sir. Thank you for this activity. And I would like to uh, introduce Dr. Aswat Babu to the participants. So Dr. Aswat Babu is from Department of Physics and from IIIT Harvard. He's a IBM certified educator in the quantum technologies. His core area is quantum information theory, quantum optics, nonlinear dynamics of optical systems, nonlinear optics, and other related areas in the quantum technologies. So, as he also already mentioned, that he will be covering several topics in this FDP. So, he will try to put up all the details of the lectures, and he will try to cover the syllabus for this. He will be taking lectures on introduction to sensing, some fundamental quantum mechanical principles, some quantum measurements to quantum photo detection. So, uh, uh, so today's talk will be focused on introduction to sensing. So, over to Dr. Aswat Babu.
Thank you, Manoj sir. So I'll start. Manoj sir. Yes, sir.
Yes, sir. Please.
Yeah, I'll start.
Please.
I'll start. I'll start.
Thanks.
Hello, everyone. Just give a minute. So I'll set up a few things for the presentation. You can see my screen. I think things are slightly down with respect to network. So I'll try my very best to ensure that things are dealt properly. Okay. Right. Audience, any issue with my audio, please say and just text it. If there is no issues, very good. we'll have it go further. Okay, great. So no issue. Super, super. Good to know that the network issue is not there. Okay, with respect to my voice. Okay, right. Yeah, straight away you see a blank screen. Please be with me. So as you can see, as per the schedule, okay. So I was asked to give an introduction to sensing, right? So introduction to, right, sensing. This is what I was asked to give, right? Sir, hope the recording started, Manoj sir. So just check the recording is going on, I hope. Right. So I was asked to give the sensing. Okay. Right. I'll try to give that. Okay. So first of all, why do I need? So you can see this is what I need. This is for this I need. I need to go for sensing in the prospect of quantum technologies. Okay. Right. So yeah, for the quantum technologies, I need a sensing. So I will just start with the very basic sensing, what we can know of or what we need to know of. Okay, right? So fine. So let me use my hand notes. Okay. So there I'll explain neatly and slowly. We have about 45 minutes time. I'll try to myself more clearer and so that you will get connected to the quantum sensors. So first of all, I would like to give some sensors. Okay, right? So the existing sensors around us, existing sensors. Okay, right? I would say around us, or I would say in real world applications. As of now, we are actually coming across them, right? We are coming across them in day-to-day life. Okay, I mean not in a home, everywhere around. Okay, right? So that is what I would discuss, and we'll see what is the limitations. Okay, we will see what are the limitations. I will call what are the limitations. Okay, right? What are the limitations? Because of that, we need to go for a better sensors beyond these limitations. Okay, right? So that is what we will do and we'll try to do. Okay, so in the case of existing sensors, okay, the first sensor we will come across in a day-to-day life or in real-world applications is the first sensor. I will call first sensor is temperature sensor. We will not go into the detail. We just see what is its functionality and what is its limitations. That is what we want to exactly know. Okay, so I will say temperature sensors, right? So where these sensors are used, right? So the very basic level, these sensors are used, okay, to measure, okay, to measure and monitor, for example, the temperature of the system, temperature of the, I would say, device. Okay, instead of calling a system, a device. Which example, right? We use a lot of day-to-day life gadgets. I will say computer. I would say computer and the CPU. and CPU motherboards gets a lot of heat. So we need to measure and control the temperature accordingly. You have to cut down the overuse of the motherboard by switching off the device, or you can add some cooling setup where the motherboard could be cooled or a processor could be cooled, right? So another place where we see temperature monitor is required is all the mechanical devices which moves are based on motors. Okay, electric motors, I will call electric motors. So these motors, we need to monitor how much heat they are being generated with the rotating pulley or anything. Okay, so this device, in these devices, we need to do a temperature monitoring. How it is done is there is something called temperature sensors, something called thermistor. Okay, you can see it's a combination of thermal effect plus a resistor. Okay, so I would say temperature sensitive motor, sorry, sensitive resistor. Basically, any material, if I take a conductor, okay, it possesses a resistance. If you increase the temperature of the conductor, as you guys know, the resistance would increase because inside the resistor there are current carrying conductors. Because of temperature, they go haphazardly and they will interact and they collide. Okay, they collide, and because of the collision, what happens? The resistance goes high and high. Okay, so just a minute, let me ensure that my video is being connected. Okay, anyway, let's not waste any more time on that. Okay, so the temperature based resistors. So these thermistors, not any regular temperature based resistors, they're actually called negative temperature coefficient based resistors. Negative temperature, okay, temperature coefficient that is called NTC, negative temperature coefficient based resistors. Okay, why the negative? As we know, the temperature is increased, resistance could increase, right? If it is, there is anything opposite of it, okay, which is opposite to the conventional resistors, where their resistance increases with the temperature. Okay, but in the case of NTC based resistor, the temperature goes down. Okay, how? I can just show you a plot. Okay, so the temperature of them, as temperature goes increasing, the resistance goes down. Resistance of the thermistors. Usually, resistance of thermistors is given with the scaled resistance at 25 degrees Celsius. Okay, right? So you can see inverse proportional. So with increase in the temperature, resistance going down. So what people do when it comes to the calibration, they will just find out by varying the temperature. They will just find out how the thermistor resistance is actually behaving. They will get the points and they will do a curve fitting. They do curve fitting, okay, to get a relation between thermistor resistance, the scaled version, in terms of exponentially connected temperature values. Okay, right? C by T square, D by T cube, and so on. Okay, where A, B, C, D are the constants, depends on thermistor properties, or you can say thermistor made up of materials. So those material properties would dictate what is ABCD. Okay. So here the problem, if you see, okay, right? So only with a certain temperature range only you can do. Okay. So that was the limitation. There is a limitation of certain temperature range depending on the material property. Depending on material, okay, property. And remember one more thing. So it's a classical effect, it's a macroscopic effect. So it is macroscopic, means collection of many charges together contributing for a sensing effect. Okay. So because of that, what happens? I would not be reduced to a lower microscopic level. I can't do that. Okay. So this is a thermistor for you. Okay. Let me give you another way of finding a temperature of, let's say, for example, okay, for example, the motherboards. So for a motherboard, the temperature measurement is actually used by done by, there is something called thermocouple. Okay. So what is this thermocouple is made up of? It will made up of two metals. Okay. Coupled. Right. So for example, there is a copper. There is a copper. There is a iron. For example, copper is there on the top. Iron is there on the bottom. So they are connected by two junctions. It's also called thermocouple junction. Okay. So they maintain cool junction at one point where we don't want to measure any temperature. We'll maintain cool, but wherever the temperature is to be measured, so that location they will put this junction. Okay. Temperature measurement junction. Okay. So with that junction, so you can measure the temperature. Fine. So now what happens if I have a couple like this? If you maintain a cool junction, means cold junction, because of temperature at the hot junction, there is a current is developed across, some kind of voltage difference is maintained or created. Let me show you that. Okay. So there is a, you can connect an ammeter. So some current would flow through, okay, because of this heat and cool junction. So how much heat and cool junctions are separated by temperature? Because of that, there is a current flow. Ammeter would show the current. Okay. So the amount of the current generated, okay, is directly proportional to the temperature or the hotness, hot or temperature at the hot junction. Okay. Right. So using that, you can measure the temperature of the, let's say, motherboard. Motherboard will have a thermocouple. One end of the thermocouple may be not in the motherboard, outside, and the hot junction inside the motherboard or on the motherboard. In that way, it will find the temperature. Okay. So this is thermocouple for you. Again, it has its own limitations. Okay. And there is a voltage or current dependence on the metals used here. Okay. So the metals used would dictate, okay, the ability. Okay. So depending on the particular metals, only we can measure particular temperature. Okay. Very tiny voltages could be measured, but not too tiny. Okay. Right. So because the temperature changes would directly proportional there. Okay. So that is one way of thermal temperatures. There is something called solid state sensors. Okay. There is a solid state. Okay. Let me write down that quickly. Solid state sensors. Okay, right? So solid state sensors are actually PN junction based sensors. Okay, right? So what is this PN junction based sensors are? As we know, the semiconductor materials can exist with the p-type and n-type. So you can create a p-n junction, p-type and type. There is a depletion layer is formed the moment you connect them. So it has some voltage difference maintained between this depletion layer. Okay, and depending on the temperature around, okay, so depending on the temperature around, this depletion layer could be varied. Okay, so how? Usually for this solid state sensor, PN junction based sensors, there is about average 1.8 millivolt variation per degree Celsius is seen. Okay, so what you can do, you can devise a PN junction or a diode based sensors or temperature sensors based on this. Okay, how? With the rise in the temperature, the electron hole pairs are actually created. Those electron hole pairs travel across this PN junction. Okay, electron hole pairs formation and current through the junction or a depletion layer, okay, could be used to measure the temperature. Okay, so these are solid state sensors. Okay, so again, wherever we could put the PN junction, only those locations it is possible. For example, in the case of IC, integrated chips, we can have this SSS, solid state sensors, at a top layer. Okay, only at the top layer, where temperature variation could be measured in terms of whatever is the voltage developed or voltage change across this PN junction diodes. Okay, so keep that aside. Again, it is the effect of macroscopic, okay, macroscopic effect, okay, giving us the sensing ability. Okay, macroscopic means several charges together giving us, okay, the effect of sensing. Okay, so these are like the temperature sensors. Okay, and what are the other sensors which we will come across is something called optical sensors. Okay, other sensors. Let me note down. Okay, so far we have seen 3 sensors, classical sensors. Let me see optical sensors. Okay, right? So, yeah, I have shared the screen. Somebody was saying, Rajan Rajeshwari ji, I have shared my screen. So please see, there is a trouble with your network or something. Okay, right? So Anjan Bhattacharya ji is also saying not visible. Please check. Hello. All right. And there is a question here. I'll quickly take the question. Let me see. Okay. Okay. What is the difference between remote sensing and quantum sensing? Is there any physical touch in case of sensing, unlike remote sensing? Okay, like remote sensing in the sense you sense the signal, send a signal to some remote location, and get back the reflected signal, and you measure it. How much is the reflected message? The info, like signal, is being changed. Depending on that, you can do the remote sensing. Okay, right? So it is nothing to do with the quantum sensing. Quantum sensing, as of now, it is being done at system level. Okay, right? So that is what Vinodji, right? Okay, great. Thank you, Nitya ji, for confirming that you can see my screen. Okay, I'll quickly see, we have only half an hour. I have to lead you to all the existing classical sensors. Okay, right? So I request the organizers at the academy to mute. There is small background. Yeah, right. So, hello.
Yes, sir.
Yeah. Sir, thank you, sir. Thank you. So something again, Shamia ji saying screen is not visible here, but in YouTube it is visible. Oh, I'm sorry. I don't know why is that so, because I have also opened as a one of the participant in another system. I'm able to see my screen in that
Sir,
system.
your screen is visible, sir.
Thank you, sir. Thank you, Manoj sir. Okay, there is one more question. Actually, any physical touch in remote sensing, but in case of quantum sensing, there is any physical touch. Oh, yeah. You are right. Actually, there will be no need of having a physical touch in case of remote sensing. In the case of quantum sensing, okay, remember we'll touch that actually as a part of quantum sensing in this entire QT. Okay, so quantum systems are so fragile. Okay, even if you come very close to the actual the signal to be sensed, even no need to have a touch, you can just go very close. With that closeness itself, you can have the effect of the signal on the probe, sensing probe, and from there you can measure what is the strength of the signal. Yeah, that is how it is done in case of quantum sensors. Yeah. Right. In a way, you can say it's not completely remote sensing because you are bringing into the vicinity, but the physical touches may not be required in the case of quantum sensors. Okay. Right. So, what is the role of vibration in sensing? Like we need to talk about a particular application based sensors where the vibrations are used. In that case only we can address that. Okay, so I don't get exactly what is the question you are asking, so Saurabh. Okay, what is the role of vibration in sensing? If there is any sensor based on vibrations, probably there the vibrations are going to be measured in terms of some frequencies. How much frequencies are generated? What is the frequency strength? Right? Or be depending on that, you can measure the signal. Okay, there is one more question here. I have a question from Sahuji. I have a question that if the act of measurement collapse the quantum state, how can a quantum sensor continuously monitor a physical quantity without destroying the physical state it relies on? Very good question, Sahuji. Okay, right? So you are absolutely right. The quantum systems are so fragile. The moment that you try to do the act of measurement on them, it will collapses their quantumness to classical form. So that is what the observation by destruction, or the destruction takes place when you make an observation. Okay, so there are ways to, without being disturbing the quantumness, you can do the measurement. There are specific strategies, something like readout ion, readout in rare earth ion based quantum memories. There is something called a readout ion. It's a very tiny test charge kind of ion. Okay, what it does, it goes near to the signal, near to the source of the signal, and extract the information without disturbing state. How? Probably some kind of a inductor, like usually inductors don't go in touch with each other. The whatever magnetic field created by one of the magnetic coil would induce some change in another coil. Depending on the change, we will measure how much is the current going through the inductor coil. Okay, so that is one of the applications of the transformers, all those things. Okay, so without being disturbing the quantumness, there are technology emerged. Without disturbing the quantumness, we can do that. Okay, so we will definitely go through the entire QT of addressing how quantum sensing is being takes place in that case. Okay, so the question for today, what I'm covering is, why do I need to go to quantum sensor when I already have a classical sensors? So I'm just listing out few sensors. So with this listing, we will just see what are the limitations. Okay, so there is something called optical sensors. What is the optical sensors? Is there is a slotted switch. Okay, so there is a LED which emits the light, okay, LED, and there is a photo, okay, this is a photo transistor, right? There is a photo transistor which absorbs the light, okay, which absorbs the light and induces some kind of a current through a transistor effect. So there may be a transistor with a collector, emitter and gate, okay. There may be emitter based emitter, collector, current induced because of light incident on the phototransistors. Okay, so now continuously light is incident, okay, light is taken from the phototransistor and measured. The moment there is some disturbance is there here, so disturbance would create a change in the light going to the phototransistor. In this way, optical sensors are used to measure the light being disturbed. Okay, so right, if you want to measure the rotation of some motor, some pulley, something in between, you can put through and you can measure. Okay, right, the speed of a motor you can find, speed of a motor, okay, could be found, right? Okay, so now again, if you see, this is a macroscopic sensors. Okay, so there is a resistance transistor involved here. Because of the transistor, okay, so this is a light based photo transistor. It comes up with its own lag. Okay, it's very slow to switch on. Limitations, very slow to switch on, very slow to switch on and off. Okay, switch on and off. So usually it takes about 80 microseconds to 50 microsecond range for doing those things. So that because of this, there is a limitation. Okay, right? So let's see what are the other sensors which we have these days. There is one more sensor which is called charge coupled devices, CCD. Okay, charge coupled devices, these are called CCD sensors. Okay, so all the cameras in our mobiles are actually is more or less based on this CCD operation. What is this CCD operation is consisting of is, there will be a pixels, semiconductor material is arranged in the pixels, okay, right? Okay, right, it's like a PN junction, a photo transistor kind of a thing. Let's say there is a light incident on a particular location, that would induce some current flow through that location of that PN junction. Okay, for example, I want to know there is a light coming in the shape of A. Okay, so all the pixels in the form of A would gets acted up, and in that way I would measure the intensity of the light coming. Here if you see, there is a problem with accuracy. If the more intensity is coming, okay, so more intensity means more exposure, okay, to other unwanted, okay, pixel regions. So because of that, there may be a chance we might make a wrong conclusions with the incident light. Okay, right? So this is light based sensors. There is one more sensor, again the limitation is coming over here. So another sensor is like mechanical strain based sensors, which are like strain gauges. So this is being used, for example, the vehicles which are like overloaded, they will have a some kind of a mechanical material, a metal, where the resistance is arranged in a helical fashion. Okay, whenever there is a weight, okay, so it alters the resistance, right? So this is again a classical effect, a classical or a macroscopic effect, okay, gives you a sensing. Okay, right? So if the resistance of the material is, let's say, if the resistance, if it is something like 100 ohms, okay, if it is, let's say, 100 ohms, right? So the change in resistance would be around 0.002%, okay, in R. So which is very, very small. We need a serious amplifying effect to measure the change in the resistance. Okay, so this is another sensor being used in day-to-day life. Okay, the limitation is there. Okay, so what else? What is the any other sensors which we have? Yes, there is something called magnetic sensors, magnetic field based sensors, magnetic sensors. I'll quickly explain what is magnetic sensors. Okay, so basically they are actually based on, there is something called Hall effect sensors, right? So what is this Hall effect is, if you just take a material, in a conducting material in the form of a slab, okay, if you connect this slab to, let's say, a positive charge, another side end of this to the negative charge of a battery, so there is a current flows in the direction from left to right, so there is a current. Now what you do is, if you induce a magnetic field through this slab, okay, right, a magnetic field, what happens, you know, there is a moving charges, there is a magnetic field which creates a Lorentz force. Lorentz force is exerted on moving charges. Okay, so the positive charges are moving. Okay, so there is a magnetic field. So what is this? Positive charge moving with velocity v, perpendicular in the perpendicular magnetic field, would create a Lorentz force. Okay, so what is the direction of this Lorentz force? You can use a left hand thumb rule. You show the thumb, the middle finger to the magnetic field, and the index finger to the current direction, and your left thumb would show the direction of the magnetic field force. Okay, so in that, what happens, the positive charges gets accumulated on the top, negative charges get accumulated at the bottom. Okay, for the negative charges, force would be FQ would be downwards. Okay, right? So because of that, what happens, there is an accumulation of charges on the top surface, a top edge, negative charges at the bottom edge. So there is a voltage difference maintained between the top edge to bottom edge. How much voltage is actually maintained, okay, between the edges is directly proportional to the current going through the slab, and also it is directly proportional to the magnetic flux through the slab. By the way, what is a magnetic flux? Okay, magnetic flux, which is equal to B dot dA, means area multiplied by the magnetic field through dot product. So this is a magnetic field. How much magnetic field is going through this slab? Okay, so here you say, depending on the strength of the magnetic field, I see the voltage. Okay, so what I can do now, I can measure the external magnetic field. Okay, application is measuring external magnetic field. Okay, how much voltage is developed across this slab? I will just directly connect. Okay, so here the limitation is only few microvolts. Okay, so again it's a macroscopic effect. And one more problem is, if the temperature is around the system is high, these things will not work. So temperature sensitive, I would say, sensitive. Okay, only particular range of temperatures I can use. Okay, and so among this, there are something called, for example, if I want to measure a rotating pulley, right, with a gears, that is actually one of the example is gear tooth Okay, Hall effect sensors. Okay, these sensors would measure with what force. Let's say there is a gear. Okay, look at something like rotating is a gear, right? So there is a Hall effect sensor, right? So there is a magnetic field, magnet. So there is a sensor, Hall effect sensor. Magnetic field lines will go through this like that. Okay. So depending on how much magnetic field actually being disturbed by the gear, okay, we will sense the change in the voltage. How much voltage is changed? Accordingly, you can figure it what is the speed of the gear. Okay, right? So if there is a problem, I can't put the magnet inside. There is something called inductor-based sensors. There is something called variable inductor or reluctance, I would say. Variable, just like inductance, there are like a reluctance sensors. Okay, so instead of having a Hall effect sensor, we'll have a coil, electromagnetic coil. Okay, and there will be a magnet, permanent magnet. So this will be sending the magnetic field lines through the coil. Okay, if the magnetic field is affected here, effect on magnetic field lines would create change in the coil. Okay, coil induction. Okay, so by knowing how much coil induction is being changed, we can find what is the magnetic field. Okay, as usual, there is a mechanical strain. There is something called piezoelectric crystals. Okay, let me quickly give that. What is the number? 6. Okay, so piezoelectric sensors. In the interesting effect of these sensors is, if you just take a material of a three-dimensional shape, let's say material like that, if you put a strain from the top, okay, for this material, piezoelectric material, it is going to create a voltage across the edges. Okay, so from this edge, there is a positive charges are generated. On the other edge, negative charges are generated. Okay, because of this, there is a voltage difference is created. Difference is induced. By knowing that voltage induced, we will find how much strain it is causing. Okay, so you see, again, this is a macroscopic sensor. Okay, so if I see in all the cases, one or the other way, there is a limitations involved in this, all the sensors. Okay, so the microscopic sensors, limitations are there with the sensitivity. Okay, I can't go to very low sensitivity because whatever the quantum systems which we are talking about, they are actually working at a single macroscopic, microscopic level. There all these sensors cannot be used. Okay, that's right. So a very basic level sensing we just saw. Now let's see what exactly quantum sensing we needed, right, for our quantum computing systems. So let me go through that. So this is a PPT for you. Okay, so here you say introduction to sensing in the prospect of quantum technologies. Okay, right? Okay, so yeah, there is a question here, how the active and passive sensors are different from these sensors that you have discussed here. Okay, so the active sensors are the something which undergo a change by themselves. Okay, passive sensors are something which induce the change somewhere else. So you can just list down among the list, like among the sensors which I have seen, like I described, in that which would fall to active and which would falls to passive sensors. Okay, so the electric sensors, yes, there are some electric sensors, probably the resistance based sensors, right? Okay, right? Okay, fine. So let me go to the some level of sensing in the case of quantum technologies, which we may be knowing or needing. Okay, here you see, we need to explore the revolutionary potential of quantum mechanics in ultra precise measurements and sensing applications. So as you can see, quantum mechanics or quantum physics allows us to have very fragile, very sensitive systems. Okay, right? So those sensitive systems, yeah. So those sensitive systems would allow me to calculate or measure even very tiny level measurements or sensitivity. So as you can see, there is a classical limitations. Traditional sensors struggle to detect extremely small changes due to noise, and fundamental physical limits are there with these sensors. Just now we saw. Now I feel that you would appreciate why there is a the fundamental physical limits are there, temperature limits are there, device location, device size limitations are there. I can't put any, let's say, hall effect sensor and go and put it a very high temperature. I can't put that. Okay, so these constraints have a long restricted in our ability to measure phenomena at the quantum scale. Okay, so these are like macroscopic sensors we can't use. So we need to go through a quantum mechanically based sensors, that is a quantum breakthrough. So here, if I have to come up with any quantum sensor, definitely that is going to leverage the quantum mechanics to surpass these classical limits, whatever we have so far, and enabling us to do ultra precise measurements that may unlock the breakthroughs in navigation and medicine and environmental monitoring and fundamental science. So I'm just listing out what are the possible applications in which we can have a breakthroughs. Navigation, GPS navigation, there are magnetometers, quantum magnetometers. In the case of medicine, there is a diamond NV center diamond based sensor where we can have a NMR based sensors. We can have a better resolution when it comes to doing scans. Okay, environmental monitoring, we can do the temperature variations. Okay, and fundamental science, for example, we want to find the properties of particular materials. In that case, the sensors are going to be very important and they may play a crucial role. Okay, so the where this quantum advantage or the limitations are going to be eliminated, because of quantum advantages we can eliminate the limitations. How? We have something called superposition. Okay, a quantum system always exists in superposition, and we can create an entanglement between two systems. And this entangled systems, even though they are physically separated, they still exist in an entanglement form, still exist in a quantum form. We can bring the one system to the temperature where the measurement or a signal which I want to measure. You can send the system one to one place, and I can keep the other system with my in my vicinity. If the change in one of the system would induce a change in the other system because of the entanglement, in that way, what we can have? We can have a measurement taking place. Like some of you are asking this situation where this may be a remote sensing or this may be a passive sensor. So why it's a passive? The actual part of the sensor which is entangled is going and undergoing a change because of the interaction with the signal. Whatever change that is going induces a change in this one, even though the other one which is in my vicinity is not gone in touch with the actual signal. Okay, right? So entanglement is actually opening up few new domains, and there is always something which always corrects us or tells us you need to have your system behave as per your wish to a certain time, the coherence time. Okay, superposition should exist for a certain time. So within that time only you can do the sensing. So that certain time is referred in terms of quantum coherence. Okay, maintaining a stable quantum states over a time dramatically improves the measurement accuracy and stability. So you are always keep in mind your quantum systems to have a particular coherence time to have a better measurement. So even though there are advantages coming in, the advantages are also in a way comes with their own catch, their limitations. So if you are able to remove those limitations and keep an eye on the limitations, you can do a much faster, like a better measurement. Okay, so here how quantum sensors work, a simple example. So what you do is you prepare a quantum state, okay, in a superposition, okay, and then the external, you bring near to the external stimuli, means external signal, that would induce a change in that system. How much change it is undergone, the quantum mechanically, the state evolution, based on that you can do a measurement on that probe and you can find out how much change, and you can just calibrate depending on the change to the induced, like a signal which is being measured. Okay, so a state preparation is involved, quantum state preparation, initial state, interaction with the system, which is, I will represent in terms of Hamiltonian. Okay, right? So as the system interacts, we will do a Schrodinger evolution, or evolution of the system, right? So which is not just exponential, so not just a H acting, it is actually represented by, I'm sorry, I need to write in terms of exponential, okay, 1 minute, exponential minus I H T by H cross. That is a unitary operator for you, where H is the overall Hamiltonian, which captures information, Hamiltonian of information of the probe plus the signal. Okay, so in that way you can measure the change in the system. What is that? You are going to get a new state psi of 2, and you will measure what is the constituents of this new state of psi of 2, how much 0 kets are there, how much 1 kets are there. That is, you will find alpha and beta. From there you would measure what is the change, what is the signal strength. Okay, right? So let me go to the key types of quantum sensors as we have these days. There is something called atomic clocks, which are so precise, they will look like they will measure the time, okay, with an extraordinary accuracy. They only lose about 1 second in every 100 million years. Okay, so you might ask a question, why do you need such an like serious accuracy? Because so this much accuracy is required in the case of GPS. Okay, right? So even a tiny change in synchronicity between our device, our mobile, to the satellite, okay, it might give us a wrong location. Okay, so that is what very important. So the atomic clocks were actually used to precisely synchronize between multiple clocks which are far away. So the sensors, atomic clocks are one of the sensors. The quantum magnetometer, earlier I said, if I want to measure the magnetic field coming out of, let's say, a human tissue, a biological part, so that is so sensitive. So we can use something called NV center based quantum magnetometer. Okay, so there you can measure. And there is something called only gravimeters. What they measure a gravitational change for a mineral prospecting, underground structure detection, and environmental monitoring application. Suppose I want to measure, I want to find what are the minerals on a particular location of a ocean test bed, we can use that. Because depending on the minerals, there is a magnetic field coming out. The change in the magnetic field, depending on location to location, you can find where the minerals are actually, deposits are there. Okay, so there is something called interferometers. So they utilize quantum interference pattern to detect the minute changes in the displacement or temperature changes or velocity changes with unprecedented precision, which is possible with this quantum interferometer, which is simply based on quantum interference effect. Okay, what is this quantum interference? Probably you might have seen through your engineering or even 11th and 12th standard using Young's double slit experiment. Okay, Young's double slit experiment, if you have seen, where the change in the path or the path change exists between two rays which are coming from coherent source, they may interact constructively or destructively depending on, okay, they're having a fixed path line depending on they're reaching at the point with particular phase. If they are completely out of phase, they destructively interfere. We'll touch something in your later sessions on this. Okay, right? So since 3:30, I'll just quickly wind up the real world impact on quantum sensing applications. Like I said, navigation, the GPS case, medical diagnostics, for example, drug design, and security and environment also. Okay, so we can have a better internet security or a communication security with the QKD based sensors. Okay, right? So there are challenges. Current challenges is the quantum sensors require careful isolation from the environment. Like some of you are pointing out, if you don't take care of these sensors, they're going to change their superposition state, their quantumness. In that case, they're actually getting destroyed. How do you measure? So you need to have a absolute isolation. Only when I need to measure something, during that time only I have to allow that this probe to interact with the signal. Okay, so advanced error corrections are also required because there are errors creeping in my calculations with the sensors. You need to do a error correction there. Or miniaturization while preserving sensitivity remains technically demanding. Like here in this case, you have to have a smaller probes, right? So for example, NV center probes are also being explored these days. Okay, so recent breakthroughs are revolutionary advances in quantum materials and quantum control systems has led to interesting applications. Improved sensor robustness is also being seen these days, and there is a serious amount of research is going on in improving the quantum sensors. Okay, so future of quantum sensing, quantum revolution ahead. You can integrate AI into this quantum sensors. You can have a better sensing mechanism, and you can have a portable sensors which could be inbuilt in drones, and you can, whenever the GPS is not working, the quantum sensors can measure the magnetic field coming from the earth. Depending on that, it can give a location, just like birds are doing their location. Okay, and the foundational impact you can have on, for example, to find better materials for the applications like say, carbon capture and all those things. So you can have with having a better sensor, you can do a lot. Okay, so I'll just skip the one slide and I'll just give a conclusion. Okay, right? So embracing the quantum sensing, okay, with the revolution, you can do a transformative measurement, and they have unprecedented precision. You can existing quantum era, you can revolutionize. Okay, and which is actually in the existing time. So we need to give a full attention to that, as we need to go and embrace the quantum computing and quantum application and advantages. Okay, so I'll just stop at this point. So I'll be sharing both this slide. Okay, so what is the quantum advantage with the quantum based sensors, and also I will share my hand notes whatever I used for today for introduction of the existing sensors in a day-to-day life. You please go through it. Okay, and whenever I come back to you people on a later stage as part of my topics, I would cover some of your doubts. Okay, so I'll just hand it over to the organizers here. Okay, Avasti sir and Manoj sir, you can take over.
Thank you, sir, for your talk. And because we have some issue with the schedule, so I request participant to just post your questions, and we will have their answers, because sir is taking another session with you, so I will share your questions to sir and they will be addressed. So thank you, Aswa sir, for your time and initiating this series.
Yes, sir.
Now I would like to introduce our another speaker today, Professor Rajan Jha from Department of Physics, IIT Bhubaneswar. He did PhD from IIT Delhi and having research interest in the area of this coupling photonic nanostructures to nanowaveguide and resonators, instrumentation for industrial application, flexible and variable photonics, plasmonics, and today he's going to introduce the overview of this sensing technology, classical and quantum technology. So, sir, without wasting time, I will request you to please
Thank,
start your session.
thank
Thank
you.
you, sir.
Thank you so much. Am I audible? Am I
Yes,
audible?
sir.
Yeah.
Yes, sir. Perfect.
Yeah.
Perfect.
So thank you, Professor Avasthi and Professor Manoj. First of all, I must thank both of you, particularly Professor Avasthi, for giving me this opportunity to present some of our work. And when I say some of our work, it do not only mean the research work, but it also means the stuff that builds our research work. So as you see, the title of today's talk is Sensing Technologies, Classical and Quantum. So my name is Rajan Jha, and this is the name of my lab, which is Nanophotonics and Plasmonics Laboratory. You can visit our website for further details. And for any query, not even today, but in later part also, if you have any query related to the talk, you can always post me on this, email ID. So before I proceed, let me just show you. This is the, our administrative building. It's look quite beautiful. This was illuminated during Independence Day, and I have not put the campus photographs, but it's really beautiful. So I also, invite you people to please visit our website as and when you get time. So let me proceed further. So the first thing that I always do is to acknowledge my group. So this is my research group currently. There are research scholars, mostly research scholars, and a couple of postdocs. And then since we are largely into experiments, so largely the lab that we have can't run without money, and therefore I sincerely, convey my regards also to all this funding agency who has been really generous in providing us a fund to do the experiment. So almost starting from DRDO, ISRO, CERB, Spark, BRNS, National Quantum Mission, MOE, and Department of Science and Technology, and all these whatever we have been doing, including today's talk. I'm thankful to my scholars, students, and all collaborators for some fellowship from Government of India like CERB Star Fellowship, and also special funding from, when I say special, it basically means quite significant amount of funding from National Quantum Mission, DST, this year. So before I go into the topic, just let me quickly tell you that what I will be talking for, let's say next 45 minutes or so, and towards the end, maybe I will try to keep some time for a quick so that I can take few quick questions. I will give you some glimpses of what sensing is about, and then what are the two paradigm of sensing, like classical and quantum sensing, how these works, and then what are the advantages you have over classical sensors by developing a quantum sensors. But honestly speaking, both has to go in hand. So it cannot that quantum sensors will going to address all your issues and classical sensors will be sidelined. It's not like that. As we proceed, you'll see that this is what the conclusion of the talk will be like. Okay. So, if you carefully see these some diagrams, what you can see here, like many times you must be hearing in news that the bridge collapsed. Now, the collapse of the bridge has largely to do with, the structural health monitoring of the bridge may not have been done properly, or if it has been done not properly, or it has not been done. So since these structural health monitoring relies on detecting the physical parameters, so therefore these are called as a physical sensor. So what one can detect while monitoring the bridge is the different strain that gets created or micro strains that get created along the length of the bridge. at different point, or some cracks which has developed. So any of these cracks start developing from a micro, it start with some micro cracks, and slowly and gradually it builds up and it leads to some catastrophic effect leading to the failure or collapse of the bridge. So these falls under the physical parameter because you try to monitor the parameter like a strain, which is a physical parameter. When you go to sensing or detecting or measuring some chemical reactions, for example, then you try to monitor the different kinetics associated with the reaction, and therefore rate of reaction, or you try to see what type of process are involved, and therefore these falls under what is called as a chemical sensing. And last few years back, we all of are aware about coronavirus, and we know that these are some spikes of those virus. As you can see from these are some spikes which are largely related to some protein, which generally gets soluble in soap, and therefore many times you may remember that during that time people used to say that rub your hand carefully multiple times and stuff. So due to these some virus or bacteria, whatever you want to detect, that fall under the category of biological sensing. So the idea is that sensing is some process where you detect or you try to measure either some physical process or chemical process or biological process. And the way you measure is that, one of these signal can, one of these changes, whether it is like a strain or rate kinetics, reaction kinetics, or let's say the presence of protein, these has to be these need to be measured in one way or the other, which can be detected. Now, what do I mean by one way or the other that can be detected? As we go with the slide, you will going to see that. But the important point is why we are so much interested, or why the whole world is so much interested in the sensing, and it has to be seen from this graph. Now you see there is sort of a exponential rise starting from. I mean, I'm not talking about way back. Of course, way back these numbers were pretty small, but just see the way things are growing with respect to this is a global sensor market. And if you can see carefully, either it is the pressure sensor or image sensor. When I say pressure sensor, we are talking about physical parameter. Image can be for all. You need not to only do physical. You can also do chemical, kinetics. You can image, or biological process can also be image, and then one can stitch those different processes, and then one can lead to identification of some of these biological entities. Temperature sensor or motion sensor or gas sensor, which Professor Avasthi does a lot of these gas sensing stuff in his lab. I've visited his lab also. Very good work by his group. And also there are other types of sensors that exist in the market, and they are huge. They are huge. Maybe we're going to discuss some of these in my subsequent talks, not today. So the way things are moving with respect to the sensors market is phenomenal, and it is expected that this will further going to get increased, and therefore the emphasis is now slightly shifting from some of the limitations of what classical sensors possess. Can it be overcome by let's say quantum sensors? So let's try to see why these sensings are important, and then you can see that whether nowadays you must be knowing that through remote sensing application, lot of environmental monitoring have been done, including the recent landslide and stuff. People are trying to do a lot of these image analysis and then try to monitor the environment. When you go to safety and security, you know that you see that everywhere, wherever you go, there are webcams placed, and all these are sensors basically. These takes the images, process it, and as and when it is required, you can use those images to identify or to address the security issues. With the advent of high-end technology, all the industrial processes are getting automated. And with the advent of AI, you know that many of these things taking the help from AI, people are trying to automate many of the industrial process. And therefore, all these different type of sensors, how much this arm should bend, what is the position it should, how close it should be to the substrate and stuff. So typically in one of these, there are minimum 200, 300 sensors that are involved. That sensors can be of different types. That we're going to talk what it can be of. Of course, all of you are aware about the communication system. All of us use a mobile phone. So communication is one way in which you can say, which also largely, you can use this process. It's not really sensing, but from the communication system, one can, also do the sensing analysis. Just to tell you that for the underwater fiber cable that is laid in Pacific and Atlantic Ocean, so these are laid for communication purposes. But then people are also trying to use them to understand or to detect earthquake type of systems. They are trying to correlate the signal that is being propagated, or they're trying to use the same optical fiber for the detection of different other disturbances that may get created on the ocean floor. Now, in near future, as we expect that things will be very, very smart, we are currently in 5G, and we expect that from 5G we can go to XG. When I say XG, this X can be 6, 7, 8, 9, that we don't know, but one can refer to a paper in Nature Photonics last year, where there is a paper highlighting that from 6G to XG. So that paper tells you how will the communication system, especially the navigation and transportation, will evolve with the help of these different type of 6G technology. So this is another area where sensing is very much important. And of course, needless to mention that nowadays, healthcare diagnostic is something which is very, very important. And nowadays, surgery and stuff are being done remotely, where you require a lot of these sensors for, And then last but not the least, one of the important aspect is quantum applications, and we'll be discussing about them as we go ahead. Okay, so how you measure these different performance matrices of a sensor? So largely, if you see that I have tried to put some of these, but there may be, depending upon what type of sensors we consider, there may be different aspects also. One of a very important aspect is sensitivity. That means how much the parameter you want to monitor, how much there is a change with how much, for some change in the parameter that want to detect, how much is the change in the signal which is being monitored. Mean to say that if it is optical signal, what are the changes in optical signal or optical signal properties with respect to the parameter that what you want to change. That is basically the sensitivity. Resolution is how precisely you can monitor. Accuracy is, you can say slightly related to resolution, but there are some difference between. And one of the most important, if the sensors has to be made commercial, is repeatability. That means you have to ensure that every time you do the measurement, it gives you the same value. This is one of a challenge which are for the sensing community, that can the sensors work over a broad range? Dynamic range means, can a sensors which work, let's say for room temperature, for example, a thermometer that what we use at home, can this thermometer be utilized to even, let's say, measure the temperature beyond, let's say, 105, 106 degrees centigrade, or can it be utilized to measure the temperature of a ice, for example, or can it be utilized to measure the temperature of boiling ethanol, for example. So it can do some, but it cannot do all type of liquid, or all type of temperature cannot be monitored, and therefore the dynamic range of a sensor becomes very important. Generally, most of the sensors that you will see in the market follow some linear relation. That means one can do the calibration using this linear relation. And how fast a sensor response is, basically, if you see the infrared thermometer that one used, it immediately gives you the measurement, but that may not be very accurate. And typically, when you do using the mercury thermometer, then you see that the response time is slightly more, but it is more accurate. So one has to balance it out, that how much time a sensor takes to respond. And then a very important parameter, especially for optical and electrical signal, is signal to noise ratio. That with respect to the signal that what we want to measure, is there any noise? And if noise is there, then what is that noise? Mostly when you do the sensors which are based on either current or let's say light, then drift is one thing which is very bothersome. That means you make a sensor, you put it on a table, and then you monitor the parameter which you want to detect for, let's say, a few days, and then you'll see that there are natural drift due to the environmental perturbations and stuff. And then those are something which one has to address before the sensors get into the market. And needless to mention that all these need to be energy efficient, and therefore power consumption are largely what is required. So this is what all the sensors has to be done, but largely it is for the classical sensors. And this is what you can see here. And this is not classical sensors. These are example of some of the sensors which are based on diamond. And these are some of the sensors which people have been using as a classical sensors. Nowadays, it has been started being used as a quantum sensor. So as I proceed, let me take you to the two different paradigm of sensors. Like if I have to broadly tell you about what are quantum sensors and what are classical sensors, then these are two paradigms. So if you see carefully, this don't get fascinated by these numbers that far larger than 10 raised to power minus. And just because we are talking about, you are talking something about, uh, uh, you know, some atoms, and typically 1 angstrom is the size, and therefore I'm just putting close to that. But it is not really very strictly to say that for larger than 10, that it means that these are bigger objects we are talking about. And when we say bigger objects, something like, you have something like big ball, or it is going up, coming down. So these, if you have to monitor these movement of these big balls and stuff, which of course are much larger than the size of an atom, then it falls largely in the domain of a classical. So you can just loosely say that if the object size is bigger and stuff, then you can monitor them using electrical sensors or chemical or thermal or acoustic. Different type of sensors can be utilized. Anything which is subatomic, or let's say within the atom, or close to that number, then classical sensors will not going to tell you. So as you can see here in this cartoon, that this is a classical picture. This guy is trying to take the dog up, so you can measure the time it is required for that. But if you take a quantum, you know that the energy level get quantized. uh, I believe that all of you know the particle in one-dimensional box. That's a very classical example of a quantum systems that the energy level is quantized. It's no longer a linear like in classical systems, or it's no longer, I should say, that you cannot have superposition of states do not play a role there. So you can see that if you have a quantum pictures, then these levels are quantized. So you exactly know something that where is like here you know exactly the position and stuff. Here you do not know whether the you can always identify the probability that what is the probability of having this particular, let's say, emojis here or here or here. So this falls largely in the area of quantum domain. And then these are some of the recent, very, very recent stuff which people are trying to make. Like I was hearing to the last talk where he was mentioning about atomic clock, the precision at which one can measure the time scale is now phenomenal. For of course for obvious reasons, as he mentioned about GPS and stuff. Quantum gyroscope is something another which area is very, very, I mean, as I mentioned, that these are all people have started working in this area. These are not yet established fully. It will take time to get established. You can just think something like that the size of abacus, which was a computing system when it started, was very, very big, close to a size of a room. Now you have a computer and laptop which you can put on your palm top, you can put on your palms. It's something like that. So quantum related systems are still considered to be very, very big as compared to the classical counterpart, which are much more compact and precise nowadays. Then you can do a lot of quantum thermometry, quantum imaging, and stuff. So these are two class. Largely, you have to keep this in mind when you have to do some subatomic, close to atomic or subatomic measurement. You need to get into the quantum domain, and therefore things become much different as compared to what you get in a classical domain. So let's first try to talk about some classical technologies or classical systems. And I believe all of you are aware about this. All of you are something like you do Ohm's law, or you do some optics. I mean, these are some of the stuff, or you do some mechanics, some measurement using specific heat measurement, depending upon what parameter you want to monitor. And these are the principles which largely get governed. And some of the measurement that you do, either you measure voltage, current, resistance, displacement, or different properties of light. For optics, like you can measure the different properties of light. So if you carefully, I mean, I have just put these things just to excite you, many of you, that you can correlate that this is what you have largely seen in either maybe you have seen by this time in the lab, or you are aware about piezoelectric effect that you can create by inducing some sort of a pressure and stuff. You can create electric current, and this is what a voltage, or you can measure them. Similarly, electromagnetic induction, Faraday's law, all of us have done that in during our high school, and later on you must have come across these also while doing the Maxwell's equation, which of course get modified by the Maxwell's in terms of displacement current to give you such type of you can measure some sort of current by inducing by changing the magnetic field. Then there are thermoelectric effect where you can have a heat source, you can have a heat sink, and you can make the heat flow, which can be measured using some sort of electrical current can be generated. The one which led to the Einstein for the Nobel Award, all of us are aware about photoelectric effect. And then, as I was just talking sometime back about mechanical deformations that can happen to a bridge leading to its collapse, one can study it carefully for doing some early predictions. And this is what all these stuff falls under the broad category of what are called as a classical sensors. So if you see classical sensors, largely most of the sensors what are available in the market relies on these electronic systems. You can have all type of sensors, whatever you use. Even you may be seeing that every day in your mobile phone there are a lot of these accelerometer. You can turn the image. You can turn the you can take your mobile phone from landscape to portrait mode and stuff if you have to view some video and stuff. So all those accelerometers and stuff are some type of electronic sensor that I needed. Needless to mention that there are tens of sensors inside any of these mobile phones. So you can do all these different type of monitoring. And nowadays, people are using this as smartwatch, which are of course electronics based, and it tells you about the different parameter of your body. This is another sensors which are electrochemical. It has certain limitations because repeatability is something which sometimes bothers. But then these are very also sensors which are people are largely using for a lot of applications, whether it is environmental or agriculture or medical. And then of course optical sensors are one which people have been using, but it has not really hit the market the way electronic sensors has hit. But I have a very strong feeling that in the coming near future, this will going to play a very important role. Not especially only optical, but it will be some optical plus electronics. So it will be something like optoelectronics based system will be in demand, or will be the requirement for the near future sensing applications. So if you just just quickly see that these are what the pressure sensor. What I am showing you now, all these are industrial applications. So there are a lot of pressure sensors. We have been doing some of these work for some of the industry in our lab. So pressure sensors is one. Similarly, you can do a lot of magnetic field sensing. These are classical sensors. Please note, we are talking about classical sensors. So either you can do magnetic field measurement, or you can do thermal imaging, or for a lot of different applications, whether it is related to industrial process monitoring or security surveillance, fire detection and stuff. So let's quickly try to see the performance of classical sensors. These are the advantages. All of us know that these sensors, classical sensors, they are very mature technology. It has been developed over more than 50 years now. Many of these things, with the advent of transistors and stuff, these sensors start getting built up. Largely the electronic sensor I am talking about. And these are widely available. You can go to any shop and then you can purchase all these small components and you can develop. Since these are widely available, it means that these are cost effective and these are simple to operate so that people can make it. These are of course robust, of course with certain limitations. Since these are robust, therefore maintenance is low, and these are highly compatible with the existing technology. But then there are disadvantages, because with every advantage there has to be a disadvantage, so that people have to move forward and to develop something which can be try to address these disadvantages. One of the major disadvantages, as I talked to you, one of the important parameter of a sensor is sensitivity. It has limited sensitivity, and when I say limited sensitivity, as we go ahead with the talk, you will realize that what do I mean by limited sensitivity. Not only sensitivity is limited, these are not very accurate. So as you know, atomic clock, the type of precision what atomic clock can give you, classical clock cannot give you. Whatever best you try to do, these get limited largely by Heisenberg uncertainty principle. So whenever you try to consider a system, it's the Heisenberg become very, very important. Of course, in quantum also it happens, but in classical systems, the typical uncertainty in energy or time that you consider is of order of typically nanosecond. However, the number sitting on the right hand side in Heisenberg uncertainty is 10 to the power minus 34. So like 10 to the power minus 9, 34 is wide apart, unlike in quantum, where the measurement technique is slightly different, and therefore you tend to push those limits. Very important aspect of any of these sensors are susceptibility to noise or especially to electromagnetic interactions. Many of these electronic sensors do have this problem of electromagnetic interactions, and those are the sometimes they are they obstruct the working of these sensors, and therefore one has to be careful. So these are data. Of course, needless to say that if you want to use some sensors which are bigger in size, these are bulky, but not as bulky as what quantum sensors exist. But in principle, it is not very convenient to take it to the field. Since you know that these are mostly based on electron, or when I say electron, of course, in chemical reaction, electron do participate, and therefore you have tendency to degrade over time. When I say degrade over time, it does not only come from uh, with classical system, that can also come with quantum systems. But if you try to use, rather than electron, if you try to use photon, that the degradation to some extent minimizes, because of these those are less susceptible to electromagnetic interference. Many times some of these systems require more energy to operate, and therefore energy consumption is another aspect which need to be addressed. So some issues of these classical sensors one can address using quantum systems, and this is what we're going to see. So the first part, this is what I was talking about, the classical counterpart. We talked about some of the limitations of these classical counterpart, what are the different ways one can monitor that. Let's talk about the quantum sensors now. So when I say quantum sensors, we have to keep these things in mind. We are talking about some of these numbers, and we know that the energy level is not as good as in classical counterpart, where you get some sort of a continuum. Here the energy levels are very discrete, and it is these discrete energy levels which exist allows us to do very fine measurement in quantum systems. Largely the quantum technology, if you see, these are the large, I mean, I'm saying largely, it is not that there can be other point also, but these are the four principles which allows for quantum technology, or which allows for the development of quantum system. But what is quantum technology? So basically you have to prepare. When you say prepare, I will tell you what it means. And you do some manipulation, and then you measure some of these quantum states. When you say quantum state, it is as good as saying those discrete energy levels. So you have to do those whenever matter or light they are interacting. So you have to do those measurements so that you unlock some of those capability which classical cannot do, right? So unlocking some of those capabilities which classical mechanics cannot do, one can do using quantum technology by by measuring these quantum states of matter or quantum states of light. So when I say quantum states of matter, like energy level are discrete, one quantum states of matter, for example. Now, how these works? The very important aspect, what makes classical different from the quantum, is that quantum systems they follow this superposition. Please note, superposition is different than addition. You superpose two vectors, but you can't superpose two scalars, right? If you have E1 plus E2, if you have E1 and E2 are two electric field, then it will not be equal to E1 plus E2. But you know that the extra term that pops up. Unlike, let's say, if you have to do some addition of any of, let's say, two of any parameter, like two numbers, then you do the addition of those numbers like directly without adding any term. So superposition is whether it is any system associated with electron or photon, it gets superimposed, and then there exists a multiple states at the same time until it is measured. So this is very, very important aspect of superposition which are utilized for quantum sensing. So another important concept is entanglement. Many of you may have heard about Einstein spooky action that you perturb one part of a system anywhere in the universe, and then it will going to get perturbed the other. It's something like, if I have to say, it's something which you can easily correlate is movie like Jurva, where two identical guy will going to get affected. If one does anything, the other feels the same. Some entangled because they are in sort of some way correlated, and something very similar here also, that you have two or more quantum particle and they are linked, such that how, no matter it is how far apart, anywhere in the universe, it will going to get caught up. This is what is called as an entanglement. Quantum tunneling is something which you can visualize, that if you take a classical particle, this is what I mentioned to my students in the class, that let's say if you it is not quantum tunneling exactly, but I'm trying to give you a feeling of what a wave particle duality can do, leading to some particle to exist as a uh, classical systems, and some particle can go into the superposed state and thereby going to a quantum, systems. So you can think that when Virat Kohli is batting, and let's say, for example, Bumrah is bowling, which can always happen in IPL. Imagine that Kohli and Bumrah, they are playing cricket. So typically the response time which you can calculate, keeping in mind the cricket yard, length of the cricket yard, the size of the bat, the weight of a ball, typically it will fall within sub-seconds. So the time Kohli get to hit the ball is typically of order of that. But imagine that if I scale down everything, when I mention, I try to scale down the two cricketer, need not, those can be anybody. The two cricketer size goes to nano dimension. Just imagine that. So now those are not a classical particle, those are the quantum particle. It may so happen that at the same time, in classical system, what you observe, that unless and until Bumrah, for example, or the bowler throws the ball, batsman cannot, it will not be on the batsman bat. It has to be released from the bowler hand, then only it can come on the batsman bat. But when you go to a subatomic systems, or when you go to a dimension which are atomic and subatomic, then there can be a possibility that ball can be at the same time in the hand of a bowler and on the bat of a batsman. And this is where you can start thinking about some sort of a superposition, a superposed state, that you have finite probability of measuring the two at the same time. Something like that. So these are some of the ways in which quantum measurement. You may be knowing that whenever you try to do a measuring of a quantum system, then it just collapse. Collapse means it will be difficult for you to measure into some other state. So it collapse doesn't mean that it fades away, but it will take some other states, and this is what you get, a unique solution. This is what it helps you to get a unique solution in a quantum systems, unlike in classical systems. So as I told you that quantum phenomena can be superposition, entanglement, squeezing, tunneling. These are all beyond classical limits. Just see carefully what does it mean. So quantum superposition can be something like, you see, these are 0 and 1. So this guy is, at both. You see, it is going 1 and also coming to 0. So as soon as it tries to do some measurement, so it is difficult to say whether it is at 0 or 1. It is in both the positions. Similarly, quantum entanglement can be, two systems are entangled. Squeeze state of light is you get a possibility or probability of measuring in one state with very high probability, and this is what you can see that the signal is getting some very strong value of psi square, which is a probability density at some particular value of x. Then you need not to worry about this spin state and coherence. Possibly as we go ahead with the talk, you will get more into this. But these are some of these quantum measurements, which nowadays is a hot topic of research. And quantum tunneling, as I was talking to you about something like some time back, that this is some electron and there is some wall. So electron can also be available on the other side of the wall. It is not unlike a classical ball. If you take ball, will always on the left side. If you have, if you are having a ball, it cannot go on the other side of a wall by penetrating through the wall. But quantum particle can be on the other side. This phenomena is called as there is concept of interferometry, which many of you may be knowing from your school days, that when you take two light beam and you try to superimpose them, then there is some redistribution of energy. Of course, you have to fulfill certain criteria like coherence and stuff. Similarly, in quantum also you do the interferometry, and one of a very important interferometer systems what people uses is called HOME or Hongu Mondal interferometer systems that are used as a quantum interferometer for to measure something like called as a second order correlation parameter that we can discuss maybe in future slides. Okay, so some of quantum systems or quantum sensors, what you can think are classical examples. As I discussed with you about atomic clock, and as I mentioned, it can be utilized for GPS, for telecommunication. All these are futuristic. People have not yet get into these. Of course, many of you may be knowing that satellite communication uh, or quantum communication between Austria and between Vienna and China was possible some years back. These are two, of course, these are country wide apart, but they can demonstrate they can demonstrate quantum communications uh, using quantum principles. So atomic clock is one of a classical example of a quantum sensors, and then quantum magnetometer. This is again a very hot topic of research in the current situation, where people try to use, generally you'll always hear from people, oh, how pure is a diamond? So when you go to a market, you want to get out 24, give me a 24 carat diamond, or the best diamond, there should be no defect, it should be a pure diamond and stuff. But for physicists like us, or those who are working in the areas of quantum sensing and metrology, the defect in the diamond is most interesting. You don't want a pure diamond. You require some sort of a defect. And one of a very important defect in that is envy centers. So it's some sort of a defect which one can excite and then do some measurement. And that measurement can give you what is called as, you can monitor very small magnetic field using such type of NV center defect in diamond. And when I say small magnetic field, I'm talking about some sub pico Tesla, or maybe close to femto Tesla. Of course, there are reports on that. One can look into the literature and can figure it out. Apart from those magnetic field, it can be utilized for NMR. This is one of a technique required for characterization of some of a material. And of course, once you have these imaging techniques, once you have such type of system, you can use it for a lot of imaging techniques. And wherever the magnetometer can be used, or wherever you want to monitor the magnetic field, one can use such type of quantum magnetometer. Another one is quantum gravitymeter. This is another very important, one of a very important area of research what people are trying to pursue. And as you can see that these are required for some of these studies like earthquake or seismic studies, volcanic monitoring, climate. I mean, a lot of applications are there, but these are some state of art what I am discussing with you. What are people are looking forward for development. It is not yet developed to extent it can be utilized in day-to-day life. Okay, so another one is a quantum gyroscope. Gyroscope is already classical. I have talked to you about, uh, gyroscope, which are in our country, we do make gyroscope, which are fiber optic based gyroscope. It is being done at one of our defense lab in RCI, and a very good colleague of mine is into it. So, but then there are requirement of quantum gyroscope for many of these applications, as you can see that. This quantum imaging is something which, if you look into the literature, there are very few papers on quantum imaging. People also say it as a ghost imaging. Then people are getting into a domain of something like super resolution. You know that there is certain limitations of 1.22 lambda by d, how small or how well you can resolve 2 points. But then people are trying to go beyond that using some of these quantum systems, thereby leading to what are called as a lidar, light ranging and detection, light detection and ranging, something like sonar on the basis of that. And another area is hyperspectral imaging. So hyperspectral imaging is a concept where you try to incident, broadband light source, and you, from the reflected from a large area like tree plantation and stuff, you try to figure out what is the vegetation like in some particular area. So this is another area which is largely required by lot for agriculture use and stuff. So these are falling in the area of what are called, people they have started calling as a agricultural quantum photonics, something like that. Quantum, pardon? So then there are certain areas called as a quantum thermometer. These are expected to we are expected to do the measurement which is not possible, which is not possible with the classical system, and therefore these can be utilized for something like scaling a temperature over very small range. How small is small? We are talking about measuring the temperature of a cell. So this is another area which is very important. So there are a whole lot of quantum applications, what people are talking about from quantum internet. If you look into a literature, there is a paper by Kimball talking about a quantum internet 2008 Nature. You can go through that paper. And there are quantum entanglement, key distribution, teleportation, topology, and computing. So these are whole gamut of quantum systems which people are thinking that they will going to come up with, and very fast. These things are changing very, very fast. So if I have to do the performance analysis of a quantum systems, of course, the advantage of these are they are highly sensitive. So please note the classical counterpart, the advantage, disadvantage, one of the important disadvantage of classical sensors or classical technology-based sensing system was low sensitive, but these can be extremely sensitive. Extremely means extremely sensitive, and therefore, since these are very, very sensitive, they can be also very, very precise. And I think the last speaker talk about some of the precision about the time and stuff, so you can just make out how precise are these. Super resolution imaging and stuff is what quantum sensors are going to give you. And many times, environmental perturbations is a stuff what people have been talking about, but these will going to overcome those limitations. And you can do a lot of non-invasive biochemical sensing. Like nowadays, a lot of people have a concern about biomedical sensing can be invasive and stuff. They have a potential to be small, but it will take time. It will take time, and therefore these are the major limitations or disadvantages that exist with a quantum sensor. And one is these are extremely costly. Doing quantum research is extremely costly, and you are aware that government of India have been very kind and they have pumped quite a bit of money into this so that country can become self-sufficient and reliant in developing some of these systems within the country itself. These are still very complex to operate. You will see that some of you can visit my lab. You're going to see that it is not as simple to develop some small measurement systems need to be very, very sophisticated. One can make it temperature sensitive. Therefore, these are also, certain systems has to be dealt at a low temperature, and there are very, very small availability in the market where commercially things are not available. You can see there are very few, not that as great. Integrating them on field is a big, big challenge, and it requires some good amount of time for development. It is still not in a stage where you can say that things have developed. It will take time to develop some of these quantum sensors. Let's quickly try to get into the comparison chart, showing you that what does the classical and quantum counterpart give. So if I have to summarize whatever I have told you about earlier, like sensitivity is here moderate, it's extremely high, precision is limited by classical noise, but it surpassed first random quantum limit by a quantum effect. We have discussed calibration, these are regular, drift prone, these are all robust. So you see that whatever the limitations exist with the classical sensors, one can overcome largely with the quantum sensors. These are scalable and low in cost, but these are very extremely expensive, and these are still not, therefore it has been written for now. For now, it is non-scalable. It is getting difficult to scale many of these parameters with the expectation what people are looking for. These sometimes classicals can be also, complex, but not as complex as what is required. These require some special type of infrastructures. These sensors are very mature. It is still emerging, as I mentioned, and therefore it is difficult. Some area where these sensors are already, we have discussed about them. These are some areas where these are already existing. And this is what people are visualizing, that where our defense can go, security, communication, healthcare, navigation, Autonomous vehicle, something very, very hot area coming up for research in near future, where quantum sensors will going to play an important role, quantum computing and information. So apart from that, just future prospects, if you consider for miniaturization, people have been talking about classical sensors using MEMS and NEMS, how low, but still you know that even if you want to these micro, mechanical and electrical systems for measurement, still those are quite significant. If you have to do, really miniaturize, then you have to get, device field deployment has to be there. People are trying to integrate IoT with classical systems, which is Internet of Things. Possibly, with quantum sensor, this integration will be easier. Here you have flexible and wearable systems. Here you don't have. People are still working on that. AI is a lot of big claims with AI for imaging with classical sensors. Here, imaging will be largely with single photon and entangled single photon for imaging. Manufacturing is easy here, mass produced can be produced, but here it is difficult. So one has to be very precise, and cost has to be come down. Environmental, these get perturbed by environment. We do expect that, even for these quantum sensors in future, quantum gravitometer for underground, even underground mapping will be possible where you don't have to dig at every place to identify them. So I think this is what I will just conclude here, that we have a long way to go before some of these quantum sensors can be utilized largely for mass scale, like our classical counterpart, and we have to yet see that how these things evolve. Okay, so what I have discussed today, largely in talk, is as follows. I try to give you a brief overview of classical and quantum sensors. Classical sensors, we have, that many of us use them. Quantum sensors still, it's confined to lab. Classical people are trying to, miniaturize, make it wearable, integrate to AI, IoT, and stuff. Quantum is yet to be done for all these different applications. And as I started my talk with that, it is not possible to have either classical or only quantum. Both has to coexist, and both will coexist in future. You're going to see that as we go ahead with the development of these quantum sensors. You'll realize that classical can't be left behind. So it will be the for what people are looking forward is to take the best of the both world and try to integrate them, so that both with very high precision, and at the same time it should be a scalable that can be utilized for these quantum applications or for classical applications. With this, I would like to thank all of you for kind attention, and intentionally I have kept 5 minutes for any questions that I can take up quickly during this session. Thank you.
Thank you, sir, for your talk. And we have a couple of questions in the chat box.
Yeah.
So the first question, should I read?
Yeah, you can.
How do this classical sensor convert a physical quantity like temperature, pressure, or motion into electrical signal?
Okay, so the point is, one has to just visualize that any of these sensors, the behind the scene, the most of the time, if you see, let me talk about electronic sensors. In the background, what is going is you have electron. We are talking about electronic sensors, electron. So let's say if you apply a pressure, if you apply any physical parameter. So if I have to talk, then you either try to measure the property that is associated with the electron in one way or the other, and the property that can be measured either in lab or on the field is one of the property of electron is voltage or current. So the corresponding parameter, and therefore I mentioned to you, please recall that you have to do the calibration of your sensors, which should be linear. What it means that for a given change in a pressure, you have to measure that how much is the current or how much is the voltage. So as soon as you do that, you can calculate the slope, and from that whenever some pressure will be applied, you can tell them that corresponding to that, so much is the change in current or voltage. And that change in current is voltage is basically by applying the pressure, you try to distort the electron cloud around a given material that has been utilized for the development of a sensor. So as you change the electron cloud, or you do some sort of a semiconductor device, you do some sort of a conduction, some electron or holes combination. So that depends that what type of sensors you are choosing. So if it is electrical sensors, then it will work slightly different. If it is electronic sensors, it will work slightly different. So the whole idea is the perturbation of the electron cloud leads to some, generation of some voltage or current, and that you try to do that voltage or current in terms of the parameter which you want to quantify. I hope I have answered it.
The second question, that is, what ratio of SNR is better for signal than noise?
Signal to noise ratio is basically, let's say, for example, if I have to give you some quick example, uh, 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 it's something like that. For example, just see that if you try to measure any parameter, let's say, for example, if you try to measure displacement, that how much object get displaced under the influence of some external perturbation, and that displacement, when you are trying to measure, then you measure either in some form of a current or voltage, or let's say some optical signal like wavelength shift and stuff. Now the point is, this displacement can also happen by some other means, which is not what you are looking for. For example, all of a sudden on that system, you have some environmental perturbations from temperature. You know that displacement can, on some small scale, displacement can also be because of temperature or pressure. Now the idea is that how good you can monitor the displacement which is due to the, let's say, the physical displacement that you want to give to a system versus the displacement that has been contributed by the environment. So if you are the signal that you are measuring, that means a current or voltage or the wavelength shift that you are measuring from the displacement that what you want to measure is high, then the noise that is being created due to the measurement in displacement by some other parameter, which is not the one which you are willing to measure, will be the noise. And therefore, you always expect that the signal to noise ratio should be high, so that you only get the measurement, whatever you want to measure, you should only get signal from that parameter and not from any other parameter.
So another question is can we implement present IoT sensors used in my lab for quantum sensing, like
No,
DS-T11
no,
Max?
no.
So participants, if you have any other questions, just please write in the chat box. So I think there is no more questions. So sir, I again thank you for your time and lecture today. So now we are come to the end for today talk, and we will continue for tomorrow. The schedule I think we have already shared. So see you all participants at 2 o'clock.
Thank you so much. Thank you so much.
Thank you.
See you.
Thank you.
Thank you.
Okay, bye.
Bye bye.
Hmm?